Let me start this one going. Right, so we got 55, and they want us to represent it in a huge, for them, floating point format. 8 bits for the mantissa and 8 bits for the exponent. Okay, so that would be like 2 to the power 127 would be the size of the numbers we could store in this format. Right, again, our first job when we got denary is to just write down, using a fixed point notation, 55. Well, this is going to take quite a few bits. So I need to make sure I've put enough columns in so I can put a positive 55 in. Okay. So 16, 32, right, 64 should be enough to be able to write down 55. Okay, so I'm going to write down 55 and I'm going to put sign bit in of 0. Positive number. Then I'm going to write 55, which is a 32. And then that's another, oh, I don't know, something or other. I can have a 16 off of that. So 32 and 16 are 48, which leaves me with 7. Double check it, add them up. So I go 16 and 4 is 20, plus 32 is 52, plus 3, so that's 55. Okay, right, that's my starting point. If I want to, I could put some fractions in there, but I don't need to. There isn't any fractional part. Okay, so that's where my binary point is. I need to normalize it. That's what they told me to do. So I'm going to come from this direction looking for duplicate sign bits. Well, actually, there's only one, isn't there? So at that point, that's where we want to move the binary point. So there's a big movement going on here. So now I'm going to move it. So I'm going to go 1, 2, 3, 4, 5, 6. I'm going to put the arrow on to show that's what I moved it. Right, it's 6. Again, this is a good example. The number is bigger than 1. So that exponent is going to make this bigger when we unnormalize it. So it must be plus, and that moved 6 times. So that's my exponent, plus 6. I'm not going to do the mantissa bit yet. I'm just going to write out the final answer for the exponent. So it said 8 bits. So I need to write down 6 in 8 bits. Well, that's 6, positive 6. I need to add a further 4 bits. If I do not write 4 bits, the answer's not right. So that's my exponent. Right, now I need to write this down. So my mantissa. So starting with the 0, I'm going to put the dot in for my sake. So I've got 1, 1, 0, 1, 1, 1. Add up the bits. 1, 2, 3, 4, 5, 6, 7. That isn't the answer. I have to have 8. Okay. Otherwise the answer's wrong. It's a process. Right. The next part of the question, quite a nice little question. He said, right, how can we still represent this number but not use too many bits? So let's have a look at the mantissa first. It's normalized, so it's as compact as we can make it, but is there anything that we can discard? Well, looking at this end, this note doesn't represent anything, so I could drop that. So my mantissa, and again, I don't just write binary numbers down, I have to label it all up. So my mantissa, I can't actually do anything about the front because it's fully normalized. I can shorten to that, so I can drop a bit. Okay. The exponent, on the other hand, there is duplicate sign bits. So on the exponent, we've actually got all those. That's the only one that actually matters. So the exponent can actually be reduced quite a lot in this particular case. So the exponent is positive, so we need to keep the sign bit. Could have been that. That's as short as it could get. Right, anyone got any questions about that? They will ask weird questions about representations, like the one we looked at the other week, where it was like, what's the biggest number and what's the smallest number and things like that in a particular format. So you can discard duplicate sign bits. If it's already normalized, there is nothing you can reduce at that side. So you're just looking to say, right, well, the last bit of this number has no purpose, so I can discard that one. So instead of using 16 bits, we've managed to compress it down to 11, which, if you were storing billions of pieces of data, actually would make a difference to storage requirements.